We will now continue with our discussion of sound and sound waves by talking about the pitch of a sound. What is the meaning of pitch of a sound? I'm sure some of you at least must have heard the word pitch, high pitch, low pitch. The quality of a sound wave which determines how high or how low the sound is, called the pitch of the sound. Now, I'm going to vibrate a tuning fork and listen to this sound. Alright, that is one sound. And listen to the next sound. Now, which of these sounds is of high pitch? You heard two sounds. Shall I repeat that? Alright, the first one. That's the first one. Now the second one. Now, look at the second one. It's a very high-pitched sound. A high-pitched sound is very shrill. A low-pitched sound is flat. You see, it's a low frequency. So obviously, pitch is related to frequency. There are some people who say that pitch is the same as frequency. But no, the physical property that determines the pitch is the frequency. But pitch is the sensation of sound you actually hear. Pitch is primarily determined by the frequency of vibration of the sound, but pitch is not the same as the frequency. While frequency is the physical quantity that determines the pitch, the sensation in a listener is what defines the pitch. What you hear. Alright, the sensation created high sound or low sound. So you must distinguish the two very well. Pitch is determined by frequency, but pitch is not the same as frequency. Well, I'm going to use this now to explain a concept in sound which is very interesting and has got very wide applications. Now, pitch is what a listener hears. If you don't hear a sound, then you have no meaning for pitch. Now, we're going to apply the concept of pitch in describing what is called the Doppler effect. This is again a common term. I'm sure many of you must have heard about this Doppler effect. Now, in astronomy, we have something called a Doppler shift, which is used to measure how fast a star is moving away from us. Redshift is Doppler shift. Alright, what is this Doppler effect? If a source of sound moves towards the listener, then the pitch of the sound heard by the listener is different from the pitch if the source is stationary. Have you ever experienced when a car blows its horn and drives towards you? Have you ever observed that or had the opportunity to hear the frequency or how the sound of a horn actually feels when the car blares its horn and comes towards you, or it goes away from you? You see, as the car comes towards you, the sound will become more shrill. Well, I made a very poor attempt there, and it goes away. So, as the source of a sound approaches a listener, the pitch appears to be increasing or rising. And as the source moves away from you, the pitch appears to be falling. Now, let me see if I can demonstrate that. I have a source of sound here. Listen to the sound. All right, see if you can distinguish what you hear now. Now, can you tell me what it is? Can you hear the pitch vary? How did it vary? Did it increase or decrease? Listen to that one more time. Well, actually the pitch was increasing. And that is similar to the horn you will hear if a car is approaching you. And try and listen to this and see if that makes a difference. Well, it's rather very difficult to hear it, I suppose. Now, what does that mean? Now, this is what happens when a car moves away. The frequency falls off. So what does Doppler effect deal with? Doppler effect deals with the apparent change in frequency as a listener hears when a source of sound is either moving towards the listener or moving away from the listener. In both these cases, the apparent frequency as the listener hears it will be different from the frequency if the source was stationary. If the source is moving towards the listener, the apparent frequency will be high. If the source is moving away from the listener, the apparent frequency will be low. Let's talk more about it. This means that the apparent frequency of the sound reaching the listener is different from the actual frequency of the sound if there is relative motion between the source and the listener. And this is what Doppler effect is. This apparent change in frequency of a sound due to relative motion between the source and the listener is called Doppler effect. All right, let's now look at this in a more broad way. Now, here is a source of sound, and these circles really represent waves. Now, look at this. This source is moving to the right, and look at the waves on the left and the waves on the right. Tell me, what is the difference there? I'm sure the difference is very clear. What is the difference? The waves on the right seem to be compressed, is that right? And the waves on the left is stretched out. The wavelength is greater on the left and the wavelength is shorter on the right. That means the object or the source is moving to the right. Now, why is the wavelength shorter on the right? That means the direction in which it's moving. You see, as the source is moving towards the listener, what happens is the number of waves produced by the source, the number of waves between the source and the listener gets compressed because the source is moving towards the listener. And that is what is happening here. That means each wave, as it reaches the listener, will be a little shorter than if the source was stationary. On the other hand, if the listener is on the left side, the waves are pulled away from the listener. That means each wave, as the listener receives it, will be a little longer than the actual wave. Did you understand why? Okay. The wave source is moving to the right. Now look at the separation between the waves in front of the source and behind it. This is the front because it is moving to the right. This is behind the source. Now, what difference you notice? We talked about it, isn't it? What does the separation between the two waves represent? The separation between two waves represents the wavelength. So, In front of the source, the waves are squeezed in. The wavelength becomes shorter. Behind the waves, behind the source, the waves are stretched. The wavelength is more. The apparent wavelength. The wave separation is the distance between consecutive crests, and the distance between consecutive crests is a measure of the wavelength. Alright. Now here I have another diagram. Now, suppose this is the listener, and here is a stationary source. Alright. Now, as the stationary source, the wavelength on the left and on the right remains the same. So, if a listener is standing here, there will be a certain number of waves reaching the listener per second. You see, the number of waves reaching the listener per second is the frequency as he hears it. Is that right? Because the number of waves per second is the frequency. Now here we have an ambulance blaring its siren and moving to the right. Now here is another listener. So there are two listeners. There is one listener to the right of the ambulance. There is another listener to the left of the ambulance. And if you notice here, the waves in front of the ambulance, between the ambulance and this listener, are squeezed. Why? Because the ambulance is moving. While it is producing these waves, it is moving towards the listener. These waves get squeezed. That means the waves that are received by this listener are these short waves. Whereas this listener, the waves are stretched. The waves are pulled away from him because the ambulance is moving away. It produces the sound and moves away. The waves get stretched. So the wavelength of the wave received by this listener will be longer than the actual wave. Now look at the difference again here. This is the actual wavelength. This is the wavelength as is received by this listener. And this is the wavelength as is received by this listener. Now look at the difference. The wavelength as is received by the listener in front of the ambulance is very small, whereas the wavelength of the wave that is received by the listener behind the ambulance is much longer. So here we have a source. Let's talk about the source moving towards a stationary listener. That means we are now going to concentrate on the ambulance moving towards this listener. Source moving towards a stationary listener. Let the velocity of the sound be v, and the velocity of the source be v sub s. So the velocity of the ambulance is v sub s, and of course the velocity of the sound is v. If the source is not moving, that is the situation on the left, the waves produced by the source will be spread out in a circle of radius v. Do you understand that? V is the speed of sound, means in 1 second the waves will travel a distance v. Now, suppose the frequency, let me give you an example. Suppose the frequency is 10 Hertz. What does it mean? What do you understand when you hear that the frequency is 10 Hertz? Well, if the frequency is 10 Hertz, it means 10 waves are produced in 1 second. That's the meaning the frequency is 10 Hertz. 10 vibrations per second. Each vibration will produce a full wave. So there are 10 waves produced per second. So the actual frequency is 10 Hertz. But if now the source is moving towards the listener, well, I said here the source will be spread out in a circle. The waves produced by the source will be spread out in a circle of radius v. So if this is the circle of radius v, all the waves produced in 1 second will be in that circle. Is that right? That's the meaning of this sentence. Now, but since in 1 second the source itself has moved a distance vs towards the listener, these waves are now compressed in a region v minus vs. I hope you understand that statement. Well, that is a very important statement, and I want you to understand that very well. All right. Now, suppose we said v is the speed of sound. That means in 1 second, you see, all the waves produced in 1 second. Suppose these are all the waves produced in 1 second. If the source is not moving, all those waves produced in 1 second are spread in a region v, because v means so many meters per second in 1 second. So all the waves produced by the source are spread out in a distance v if the source is not moving. There you are. But when the source is moving to the right with a speed v, all those waves are now compressed in a region v minus vs. You understand that, don't you? There you are. These waves are now compressed in a region v minus vs. Now this is v, this is v minus vs. So all these waves which were originally spread out in a distance v are all now compressed in a distance v minus vs. Now, if f0 is the actual frequency of the source, there will be f0 waves produced in 1 second. And all these f0 waves, now here are the f0 waves. All these f0 waves are now spread in a region or in a distance v minus vs. And therefore, what is the apparent wavelength of each wave? The wavelength of each wave reaching the listener now will be these many waves, f0 waves, spread in a length v minus v0. That means the length of each wave reaching the listener now will be this distance divided by the number of waves. If lambda prime is the wavelength that reaches the listener, that lambda prime will be this distance divided by that number of waves, which is f0. f0 is the actual frequency of the source. And look at the way a mathematical manipulation I did here. I factored out a v from here. Now, is it possible for me to factor out a v from these two terms? Yes. But all I did is, watch what I did here. I just multiplied this vs by v and divided it by v. So, I just multiplied by v and divided by v, this term. And that way I created a v that is common factor. I took it out. Remaining here will be 1 minus what remains here is vs divided by v. So this v minus vs is the same as v times 1 minus vs divided by v over f0. And that is the apparent wavelength that is reaching this listener. Okay. AY. Now, if f prime is the frequency as the listener hears, if f prime is the frequency that the listener hears, what will be f prime? F prime will be v divided by lambda prime. And the lambda prime is this. So let's replace this lambda prime by this quantity. That would be v divided by lambda prime is v times 1 minus vs over v over f0. And you can see why I wrote it like this. You can see that v and v will now cancel. This f0 will now go to the numerator. That's equal to f0 divided by 1 minus vs divided by v. What does vs stands for? The velocity of the source, and v is the speed of sound. This is the frequency that is actually heard by that listener, or we call it the apparent frequency. Why do we call it the apparent frequency? Because this is not the actual frequency of the ambulance siren. It is the frequency as is experienced by the listener. You see the difference between actual frequency and the apparent frequency. The frequency as is heard by the listener, which we call the pitch of the sound he hears. The pitch of the sound he hears is higher than the actual pitch. Alright? And we can simplify it as taking v as the common denominator, f0 over v minus v, vs over v, and we can write it if we want like this. F prime equal to, this v will go up. It will then become v over v minus vs multiplied by f0. But I prefer just to hang on to this equation. F prime equal to v f0 over 1 minus vs over v. Now, this is the case where the source is moving towards the listener. Alright, the second case, the source moving away from the listener. What happens when the source moves away from the listener? What is the situation now? Now tell me, what difference will there be when the source is moving away from the listener? Well, when the source is moving away from the listener, the waves in front of the listener get stretched. In this case, the waves are stretched out in a region V plus Vs. You see, because there is more space for the waves because the source is moved away. And the apparent frequency can now be written as, you see, if you go back and look at the old equation, the denominator was 1 minus Vs over V. So the only difference here is that in this case the denominator will be 1 plus Vs over V. The apparent frequency as is heard by the listener now will be f prime equal to f0 divided by 1 plus Vs over V. That will be, again I can take V as the common denominator. This will become V plus Vs over V, and the V will go up. It will become V over V plus Vs times f0. Now I'm going to give you a couple more equations. We are not going to bother about deriving it. Listener moving towards the source. Now will that be different? This time the ambulance is going to stay in one place and the listener is going to move towards it. What will be the apparent frequency? The apparent frequency of the sound is given by f prime equal to f0 times 1 plus Vs over V. Alright? Keep track of these equations. It will be useful when we need to solve problems. Now, listener moving away from the source. What happens when the listener moves away from the source? The apparent frequency will be given by, the only difference is, this plus will become minus. So f prime is f0 times 1 minus Vs over V. We have 4 formulae. What is the first one? The apparent frequency that a listener hears when a source moves towards the listener, and that apparent frequency will be f0 divided by 1 minus, not this one, for that this plus will be minus, 1 minus Vs over V. That will be the apparent frequency as the listener hears it. Now, this is the apparent frequency as the listener hears it for the source moving away from the listener. And this is the apparent frequency when a listener moves towards a stationary source. And this is the apparent frequency when the listener moves away from a stationary source. Alright, so keep track of these 4 formulae. Write them down so that you become familiar with it. I don't want you to learn them by heart, because you know you can keep all these formulae with you when you solve problems. Alright, let's do this simple problem. A source of sound that emits a sound of frequency 200 Hertz. That is the actual frequency of the source. We call it f0. So you have f0 is 200 Hertz. Moves towards a stationary listener. A source moving towards a stationary listener with a speed of 80 meters per second. V sub s is 80 meters per second. If the speed of sound is 340 meters per second, find the wavelength of the wave between the source and the listener. Wavelength, you mean the number of waves will now be squeezed in a region V minus Vs. So the wavelength will be V minus Vs, that is the distance, divided by the number of waves. The number of waves is the frequency, which is 200. Is that right? Find the frequency heard by the listener. What is the apparent frequency as is heard by the listener? Alright, let's pick the data. f0, the actual frequency of the source, is 200 Hertz. The speed of the source is 80 meters per second. Speed of sound is 340 meters per second. As the source produces 200 waves in 1 second, that's the meaning that the frequency is 200 Hertz. These 200 waves are compressed in a region of length V minus Vs, which is V is 340, Vs is 80. So these 200 waves are compressed in a region 340 minus 80, that is 260 meters. So 200 waves are compressed in a length 260 meters. What is the wavelength as the wave reaches the listener? The wavelength of the wave between the source and the listener is V minus Vs divided by f0. That will be 260 meters per second divided by 200 per second. That is 1.3 meter. That is the wavelength that reaches the listener. Alright, we now need to find the frequency as heard by the listener. Well, it's now simple. The frequency heard by the listener is f prime equal to V over lambda prime. We don't need to use any of the other formula. Why? Because we have calculated the lambda prime. Because we have lambda prime, we can find f prime equal to V over lambda prime. That is 340 meter per second is our V. Lambda prime we calculated as 1.3 meter. Therefore, the apparent frequency as heard by the listener is 261.5 Hertz. Now look at the difference. The actual frequency is 200 Hertz. The apparent frequency as the listener hears it is 261.5 Hertz. Okay, let's do another problem. If the listener moves away at a speed of 80 meters per second from a stationary source that produces a sound of frequency of 200 Hertz, what is the frequency heard by the listener? Now remember, if the speed of sound is not given in a problem, you can always use it as 340 meters per second. So the speed of the source is 80 meters per second. The speed of sound is 340 meters per second. I haven't given it in the problem, but you must be able to use that. The actual frequency of the source is 200 Hertz. For listener moving away from the source, what is the formula for the apparent frequency? Can you look back in your notes and look for that particular equation? Frequency as heard by a listener who is moving away from a stationary source. That will be f prime equal to f0 times 1 minus Vs over V. We have all these values. We have f0, we have Vs, and we have V. So put them all in its appropriate place and calculate it. You can see, once you know the formula, the problem is solved. Okay, let's do another problem. A radar device emits microwaves with a frequency of 2 gigahertz. 2 gigahertz is 2 times 10 to the 9 Hertz. When the waves are reflected from a car moving directly away from the emitter, a frequency difference of 293 Hertz is detected. Find the speed of the car. So, you have a policeman standing here with a radar device, and it emits microwaves from the radar. That means this is the source and the car is moving away. Is that right? The car is the listener. That means the frequency as received by the car will be less than the actual frequency. Now, that microwaves get reflected from the car and is received back by the radar. That means now the car is the source. We have a source that is moving away and a listener who is stationary. So this problem has 2 parts. Let's break this problem into 2 parts and see how we can solve it. We have to break this problem down into 2 stages. What is the first stage? In the first stage, the car receives the transmission from the radar gun. That means the radar is the stationary source and the car is the moving away listener. In this case, the car is the listener moving away from a stationary source. Alright, what is the formula for the frequency as is received by a listener moving away from a stationary source? The waves here are not sound waves, so we don't need the speed of sound in here. The waves are electromagnetic waves, like light or heat. Now, what is the speed of light or electromagnetic waves? The speed of electromagnetic waves is 3 times 10 to the 8 meter per second. So, here, this is the speed of light, which is the same as the speed of microwaves. Now what are we looking for? We are looking for the speed of the source. Alright, so here again we have the data. What are the data? The speed of the speed of the waves. The waves are actually light waves or microwaves. And the speed of the waves is 3 times 10 to the 8 meter per second. The speed of the source we want to find. That is what we need to find. The frequency, the actual frequency of the radar is 2 times 10 to the 9 hertz. F prime is the frequency received by the car. Alright, let's first of all obtain an expression for F prime. Well, can you see the car moving away? It's on the corner of your screen. You may not be able to see this. So we need to find F prime, the frequency that is received by the car. The car is the listener moving away from the source. Therefore, if F prime is the frequency, it is given by F prime equal to F0 times 1 minus Vs over V. Now, F0 is 2 times 10 to the 9. Vs we need to find. And V is 3 times 10 to the 8. And that is our F prime. Alright. The car is the listener moving away from the source. So these waves of frequency F prime are now reflected back. Now, the frequency that is now given off by the car are of this frequency. Now, the second stage, what is the second stage? The car is now the source. In the second stage, the car is the source, which gives off this frequency, F prime. In other words, in our original formula, F0 stands for the actual frequency given out by the source. Here, the frequency given out by the source is this F prime. So, the car is now the source, moving away from the listener, emitting the waves of frequency F prime. The car is now emitting that frequency F prime, and the radar or the policeman is detecting it back. Let the frequency of the reflected wave detected by the radar be F double prime. Now, F double prime is the frequency as is received by a stationary listener, and the source is now moving away. So here, for a source that is moving away from a listener, F double prime equal to F prime over 1 plus Vs over V. Is that right? This is the equation we just about 10 minutes ago derived. This is the equation for the frequency received by a stationary listener when a source that is moving away gives off this frequency. This is the frequency given off by the source that is moving away with this speed. Alright, what we now going to do is, in this equation, we're going to replace this F prime by this value. Look at that. F prime is this quantity. So we will replace this F prime by that quantity. Let's do that in the next slide. Now you can see this is our F prime, and this is the F double prime. You can see F double prime is the frequency as is received by the policeman in the radar. And in the question, in the problem, it says the difference between the actual frequency sent out and the frequency received is 293. That means F double prime, this 2 times 10 to the 9 is the actual frequency. Minus this is 293. That means F double prime equal to 2 times 10 to the 9 minus 293. I hope you understand that. You see, 2 times 10 to the 9 is the frequency actually sent out by the radar. F double prime is the frequency that is received by the radar. The difference between these two is 293. Therefore, we say F double prime is the actual frequency minus the difference between the two. Is it all right? And this is the equation we had in the last slide. F double prime equal to F prime over 1 plus Vs over V. Now, this involves a little mathematical skill to solve this problem. Now, in here, F double prime can be replaced by this, 2 times 10 to the 9 minus 293. Is that all right? I think it is slightly out of the screen for you. I'm trying to get it back on the screen there. Now, this F double prime will be replaced by this value, 2 times 10 to the 9 minus 293. And this F prime will be replaced by this quantity. Let's do that. So, 2 times 10 to the 9 minus 293 equal to, that is this quantity. F prime is replaced by this, 2 times 10 to the 9 times 1 minus Vs over 3 times 10 to the 8 all over 1 plus Vs divided by V. V is 3 times 10 to the 8. Now, I'm sure some of you will get intimidated by seeing these figures. Now, is it possible that we can solve this equation now for Vs? You can see Vs is the only unknown quantity in that equation. So all we need to do is persevere and simplify. Let's do that. Alright, left hand side, let us leave it like that. Right hand side over here, see what I did? I took 3 times 10 to the 8 common factor, and the numerator now becomes 3 times 10 to the 8 minus Vs all over 3 times 10 to the 8. That's okay? This is simplified by taking the common denominator. Similarly, 1 plus Vs over 3 times 10 to the 8. 3 times 10 to the 8 is the common denominator. So that will be 3 times 10 to the 8 plus Vs all over 3 times 10 to the 8. And if you notice now, this 3 times 10 to the 8 will cancel with that 3 times 10 to the 8, leaving us on the numerator 2 times 10 to the 9 times 3 times 10 to the 8 minus Vs over this quantity. There you are. I just gave you those. These two are cancelled. On the numerator you have 2 times 10 to the 9 times 3 times 10 to the 8 minus Vs. And on the denominator we have this quantity. There we are. Okay, what do we now do? Our left hand side is, you can see, I'm going to divide both sides by 2 times 10 to the 9. You see, when I divide both sides, the left hand side becomes, this is the left hand side. Divide that by 2 times 10 to the 9. When you divide the right side by 2 times 10 to the 9, they will cancel. The right side now becomes 3 times 10 to the 8 minus Vs over 3 times 10 to the 8 plus Vs. Okay, you can see the steps that we are taking. I'm going to now leave it for you to solve that. This is now simple to solve. Vs is the only unknown. I solved it. I got 22 meters per second. I tell you, most of you have graphing calculators which will solve equations like this. If you have difficulty solving it on your own, put it on the calculator. It will solve it for you. Okay, that is a challenging problem. Let's try another one. A physics student walks down a long hall carrying a vibrating 512 Hz tuning fork. The end of the hall is closed so that the sound reflects from it. So as the student walks down the hall, the sound gets reflected from the wall in front and is received by the student. Now, the student hears a sound of 516 Hz from the wall. All right? Now, how fast is the student walking? Well, this again is a similar problem, but its complexity is not as much as the one we did earlier. The actual frequency of the source, the frequency of the tuning fork, is 512 Hz. The speed of sound, this time it is sound, speed of sound is 340 meters per second. F double prime is 516 Hz. What does that mean? You see, this again you need to break it into two stages. The first is, there is a source that is moving towards a stationary listener. Who is that stationary listener? The wall. The wall in its turn, in stage 2, the wall reflects that sound back to the student. Now in the second stage, the wall is the stationary source and the student is the listener who is moving towards that source. And the frequency as is heard by the student is 516 Hz. That is F double prime. Okay. Vs is the speed of the student. So here again, this problem has two parts. What is the first part? In the first part, the student is a moving source and wall is the stationary listener. Now, what is the equation for the frequency as is received by a stationary listener when the source moves towards it? Can you recall that formula? The frequency f prime received by the wall is f prime equal to f0 divided by 1 minus Vs over V, where you know f0, we know Vs, we know V, the speed of sound, we don't know Vs. Alright, that will be 512 divided by 1 minus Vs over 340. Is that right? f0 divided by 1 minus Vs over V. That is the frequency as is heard by the wall. Now, in the second part, the wall is the source which emits this frequency f prime. This is the frequency received by the wall which is reflected back to the listener. So this f prime is now the frequency that is emitted by a stationary source and the student is the listener. We have the case where the listener is moving towards a stationary source. What is the frequency that is received by a listener moving towards a stationary source? If f prime is the frequency heard by that listener, then f double prime, not f prime, f double prime equal to f prime times, what does f prime stands for? The frequency that is emitted by the wall, which is actually this. So f double prime equal to f prime times 1 plus Vs over V. Well, that is f prime times 1 plus Vs over 340. Alright? We can now replace f prime by this quantity, and f double prime we know. F double prime is given to us. So we will do that in the next slide. Look at again, what are the things that we know? We know f0, we know V, we know f double prime, and we know f prime equal to 512 over 1 minus Vs over 340. And this is the equation we have now. F double prime equal to F prime times 1 plus Vs over 340. What do we do now? We know our F double prime, and we know F prime is that relation which we're going to replace there. So 516 equal to, this F prime is replaced by this quantity, 512 divided by 1 minus Vs over 340 times this 1 plus Vs over 340. Alright, can you help me now solve for Vs? Vs is the only unknown quantity there. Alright, what I can do now is, that will be this quantity equal to, that will be this, I'm going to simplify the right hand side. That will be 512 over, look at the way I simplified this denominator. Took 340 as the common denominator, and that becomes 340 minus Vs over 340. That is this quantity. So this now becomes 512 divided by 340 minus Vs over 340 multiplied by, again this is simplified by taking 340 as the common denominator. That becomes 340 plus Vs all over 340. That is this one. Okay, can you simplify this? Where does this 340 belong to? You see, a number divided by a fraction. This will now go to the numerator. And when this goes to the numerator, that will cancel with this 340. So actually, this 340 will cancel with that 340. So what is left here is 512 times 340 times Vs on the numerator, and the denominator is 340 minus Vs. I hope you understand that. This 340 will cancel with that 340. So my numerator now is 512 times this quantity, and the denominator is this now. Okay, now what I'm going to do is I'm going to cross multiply. This denominator is multiplied by the numerator. You see, this quantity is equal to 516. So 516 multiplied by 340 minus Vs equal to 512 times 340 times Vs. Do you understand that? Let me just write that step for you. You see, this is actually 516 equal to 512 times 340 plus Vs over 340 minus Vs. What I did is just to cross multiply. So this step is 516 times this quantity equal to that quantity. And now we distribute and simplify. I have done these steps for you. Distribute 516 times 340 is this big number, minus 516 Vs equal to 512 times 340, this big number, plus 512 Vs. Well, this is now elementary algebra. Combine terms in Vs on the right side and the numbers on the left side, and that gives me 1360 equal to 1028 Vs, or Vs equal to 1.32 meter per second. Now, it has been a very good problem. I love this problem. Okay, I want you to go through this one more time and try and do this on your own. Well, I think we have a fair description of Doppler effect and how that can be used in solving problems. Alright, I'm going to stop this lesson here, and there is one more lesson left in Unit 1, and I will get back to you with that lesson a little later. Alright.